demo we got that's sitting on your sitting on all the chairs. Have Mr. Jim West come on board.
Hello, everybody. Some of you have these. I need some help passing these out to the folks in the back rows. Should I get out to everybody? What I need everyone to start doing now while I'm doing my slides is, you have these sheets here, these activity sheets. We're going to do something with our hands today. So fold it in half, separate the page in half, and then use your fingers or a pen, pencil, and try to take out those darkened squares. I know it's going to be very crude, but that's the best we have for today. So while you're doing that, I'm going to go ahead and go into my presentation on encryption. So my name is Jim West. I'm a subject matter expert in information security. I am a CISO, Europe, Middle East, Africa. Next slide.
And you used to work here, Jim?
Yes, I did. I used to work in the G6 cybersecurity team. Cryptography, everyone knows something about it, right? Between algorithms, secret, classifications, codes, encryptions, etc., ciphertext, plain text. Next slide. So what is it all about? Some of my text is dark in there. Essentially, in a nutshell, information needs to pass from one entity or person to another, and sometimes they don't need anyone else intercepting that information. Here's a pathway from plain text getting encrypted to ciphertext for confidentiality. If you add in things such as message digest to improve and add in data integrity, spacebar again. This is my labeling method by only encrypting the ciphertext you get confidentiality. By adding a message digest, you add an integrity factor. And then of course, if you're using digital signatures, you're now employing a PKI type system to which you can employ CIA in your strategy. And of course, if you're using authentication, you can increase your integrity and availability. Hopefully everyone's got that. Just to give a brief history, my slides are not displaying fine, but that's okay. Morse code. Everyone familiar with Morse code? All right. So that was a form of encrypting information. During World War II, we had the Navajo code talkers. Or was it World War I? I'm sorry, my history is slipping me. Anyone? World War II, thank you. So the Navajo code talkers, using their language, which was not known by the Germans or the Russians or anyone else, was very important for our operations. Anyone know what this is? World War II as well. Enigma. This is one of their digest sheets, or rather ciphertext. Of course, Alan Turing invented his code-breaking machine. It was called, anyone know the name of the machine?
The bomb.
Huh?
The bomb.
Yes, thank you. And of course, since then, mathematicians have been involved in crypto, and of course we have these algorithms, RSA, we have Diffie-Hellman, we have all of these mathematicians now that are coming up with very complex mathematical problems to help obscure and hide our information. These are the current DoD standards for encryption. AES is a symmetric-based one, but you'll notice on the list the rest of them are asymmetric. Does anyone know the quick difference between symmetric and asymmetric? Anyone? Yes?
Symmetric is no sign the same key. Asymmetric is one key converts to the other key.
Thank you. So in the symmetric system, the problem with it gets very cumbersome because you have to take that shared secret, if you will, and add to hand, pretty much almost equivalent handing it to everybody. Asymmetric, you see some of the new standards here. The P384 can protect up the top secret. When you get down to the RSAs, they need a 3072-bit to go up to top secret. Okay, I'll talk about this. This is actually from the NSA's page. Anyone ever heard of Sweet B cryptography? Okay, a couple hands up. Okay, so Sweet B cryptography was supposed to be the new wave of crypto algorithms used, but then a couple of things have changed. Edward Snowden, of course, revealed in some of his releases that there are vulnerabilities to some of the Sweet B algorithms, which cause a lot of corporations to shy away from it. Also, there's quantum computing that's on the horizon. So everyone's trying to be the first to develop a quantum CPU. And so now the rush is to try to define or develop quantum resistant algorithms. So now the NSA has put out on their site, it's public, to say that if you haven't implemented Suite B, hold off and wait to spend your money on what's coming next. Okay, so with our hands-on demo, has everyone got their sheets torn? At least most of the holes poked out? Okay, so what we're gonna do is this, we're gonna treat the bottom part, or this is your ciphertext, okay? There is a message in here. And so what I've given you in the other part where you punched out with your fingers is the key. What I'm not gonna give you right now is I'm not gonna give you the starting position. But if you consider this as a 4x4, there's actually, on the one side of the key, you can rotate it 4 times. 1, 2, 3, 4. You can flip it over and also rotate it another 4 times, potentially having 8 positions. And with 4 letters and 8 positions, you can do the math. But I'm going to give you a hint. Only one side of your key will be used. So that's one hint. And then it's up to you to determine what is the starting position. So you have 1 of 4 starting positions. And once you rotate it clockwise from wherever the starting position is, you should be able to spell out the message. I'll give you all about 3 minutes. And in 3 minutes, just to kind of let you know, a crypto analyst would be able to solve this in less than a minute. Or people that play word jumbles, they might be able to also solve it. Raise your hand. Okay, great. Now I'm going to give the rest of the audience the starting position. Now, do more people have it now? All right, here we go. Revelation is, the message is unencrypted words. Very good job, sir. So again, how many folks found this somewhat difficult? It's okay.
Yeah.
Okay. And that's okay because, cryptography is supposed to be a little bit difficult. But thank goodness we don't actually rely on this type of crypto system. Actually, this is a very basic one. What I'm going to show you now, switch over to the first page. So with computers, we're able to do very complex mathematics in a very rapid and quick time frame. Here I'm going to do a PKI. This is a simple algorithm. Just hit generate keys. Okay, so now what we have is we have a key pair. We have a public key and a private key, okay? Let's type a message, welcome to Cyberbowl. Okay. Can anyone tell me, if you're about to send this message to someone, which key would you use to encrypt it? Okay, I hear public and private. Can we get a consensus with the crowd?
They're public.
So you use the person's public key. So let's take the public key, which is, can't read that, is that 161? The public key, and then hit the button for, is that encrypt message? Right there? Okay, now we see a string of numbers here. So that processes up pretty instantly. Now we're going to decrypt the message, and down here we would have to put which key now? If we use the person's private key. So the private key gets inputted and hit decrypt, and then there's a message back. So plain text to ciphertext, back to plain text. Let's go to the other one. So this was a basic algorithm. Actually, the next one is RSA. RSA is all right, so what I've already pre-put in here is a random seed, which is just a random scattershot grouping of numbers. So we have there at the top, which we're going to use the basis to generate the key bits. So let's hit the drop down on the 512. Let's go for the max, which should be, 1020, yeah. Okay, so hit generate key. Takes about a second, a little bit less than a second. All of a sudden it's did all this factoring based upon that random seed. So now we're going to use this information that it just outputted for us to encrypt messages with. So if we go down there to the plain text box, let's again type "Welcome to Cyberbowl." And then hit the encrypt button. So it uses the information that it just output here for the prime factors and to generate the ciphertext. And that's a lot more complex than the other algorithm we just used. Now what we'll do is delete the plain text "Welcome to Cyberbowl," the line above. So now we don't have the plain text, we have the ciphertext, but because we have the key, hit the decrypt. And in less than a second, it got us back. Okay? All right, so back to the slides. Any questions on that so far? Yes? Yes? Oh, fine, okay. So, we already talked future crypto. How many folks have heard about commercial solutions for classified? Okay, quite a few hands. So, one of the quick things I want to show is the use of encryption in this integrated solution. Here we have the end user device, WPA2, and then we have a VPN client, both with encryption measures connecting to the black and eventually to the other end of the gray to enter the unencrypted red. You see the two lightning bolts here for the different encryption standards. You'll notice that one is AES, which is a what crypto system? Symmetric. And then on the second, on the gray, we have asymmetric. Why do you think that is? Why do you think the NSA planned it that way? Two fundamentally different crypto systems. One asymmetric, one symmetric. And again, I'll do my overlay with my CIA method. Obviously, encryption is confidentiality. And then when you get to the driver itself, it's more integrity, availability at the hardware level. For the VPN, the core principle for VPN is availability. That was a discussion we had this afternoon. And then, of course, you add your integrity with your IKE, etc. There's a more detailed version, which I got to speed it up, I'm told. There's my labeling. We already did the demo. Thank you very much. That's my encryption. That's all the time I have.
Cool. All right. Thank you. Okay.